Let's see now what happens when we have an example with friction. In this problem, we have an object with a mass of 50 grams that slides down the spherical surface with a radius of curvature of 2 meters. That surface is not smooth, so we have to actually take into consideration the presence of friction. The object starts from rest at location A, and at the time it reaches the bottom, location B, it is moving at a speed of 6 meters per second. The question here is, what is the work of the friction? Let's choose a ground, just as before in the previous examples. If we're going to work with the total mechanical energy, we will need to write the formula for the potential energy, which always requires us to be very explicit about our choice of ground. If I choose for the ground the bottom of that spherical surface, that means the original height from which the object starts is HA, here marked on the diagram, equal to 2 meters, which is equal to the radius of that sphere. With that, I can actually write the total mechanical energy of the object at location A. It's going to be equal to the sum of the kinetic and the potential, or in other words, it's going to be 1/2 of mv squared plus mgh. Now here, let's remember that the problem tells us that the object starts from rest at location A, which means that I can set up VA here equal to 0, and I can see that the total mechanical energy will be really equal to the potential energy with which I started at location MGH. Now let's look at what happens at what energy I have at the location B and the bottom of the spherical surface. Total mechanical energy is going to be the kinetic plus potential, or in this case will be 1/2 mvb squared plus mgh. H here is the height of the bottom above the ground. But again, I chose the ground to be exactly at the bottom of that surface, so that means that the height here is going to be 0, and the total mechanical energy is going to be simply 1/2 of mv squared. Here v is the velocity of the object at the location B at the bottom of that track. Now we're going to apply what is called the work energy theorem in the books. I call it here the work energy relation. That tells us how the energy changes in the presence of friction. We cannot really say that the energy is conserved. We cannot expect that the energy at location A is going to be equal to the energy at location B. In fact, we know that the energy at location B is going to be probably less, because the effect of friction is to actually remove some of the mechanical energy from our system. And that is what is known as the work energy theorem. I will write here that delta E is going to be equal to the work of the non-conservative forces. Remember here, non-conservative forces refers to all forces except for gravitation and the elastic force of a spring, at least in the physics 1. For our particular example here, the work of the non-conservative forces here will be simply the work of friction. So I can actually write that the difference between the mechanical energy at location B, which is our final destination, minus the mechanical energy at location A, which is our original location, has to be equal to the energy that the friction has removed from our system. Here it's called the work of friction. With that, I can write that the energy at location B, which is 1/2 of mvb squared, minus the energy at location A, which is mgha, has to be equal to the work of friction. And this equation actually will give us the answer for what the work of friction in this problem is. I'm going to move the symbol for the work of friction on the left, and I'm going to replace all the symbols with the numeric values given by the problem. So I'll have the work of friction is equal to 1/2 of 0.05 kilograms. Notice here I switch to the metric system. 50 grams is 0.05 kilograms, multiplied by the speed at the bottom, which is 6 squared, minus the energy at the top, which will be 0.05 kilograms times g, which is 9.8 meters per second squared, times the original height from which the object begins to slide, which is 2. That gives me, for the work of friction, 0.90 joules minus 0.98 joules. So I can see that my mechanical energy at the bottom is less than the mechanical energy at the location A, and the difference is minus 0.08 joules. In other words, friction has removed 0.08 joules from our mechanical system.